So recently a paper of mine called Non-Markovian Quantum Heat Statistics with the Reaction Coordinate Mapping was published in Quantum Science and Technology, and it was done in collaboration with my two PhD supervisors, Iles-Smith and Ahsan Nazir. And essentially what I want to do is make a video, or maybe a series of videos, talking through the paper, the ideas behind it, and the conclusions that we can draw from the work that we do in this paper here. The reason I want to do this is because papers are difficult to read. It can take a long time to fully digest what is said by authors of a paper that you're not particularly familiar with. And I want people to understand the work that I did. And I think that making a video like this will be useful for people who decide to read this paper. And additionally, somewhat selfishly, I know that I'll get a lot from making a video like this because trying to explain complex ideas through video is very difficult, possibly even more difficult than writing about it. So the big picture behind this paper is that we want to use what's called the reaction coordinate mapping to calculate something called quantum heat statistics in what's called the non-Markovian regime. So I'll explain what all these terms mean in due time. But essentially what we're going to do is we extend a known and well-used master equation called the reaction coordinate master equation, and we extend it such that it's able to count heat statistics or heat transfer between an open quantum system and the environment that it's coupled to. Now we compare this method that we've come up with an analytical result so that we can show that it was working as it should. And then we use our method to test two possible definitions of heat. And then we make arguments about which one is better suited to the situation that we're currently looking at. Now, why do we want to do any of this? Well, because heat in quantum mechanics is not well defined and it's very ambiguous. It depends on the particular situation that you're looking at. Now, why do we care about this reaction coordinate mapping? Well, it's very useful. It can be used to track properties of open quantum systems in the non-Markovian regime. And the question that we are trying to answer is, well, can we use this reaction coordinate mapping to track thermodynamic quantities as well? So we want to see, can we track heat statistics, heat transfer between the open system and the non-Markovian bath that it's interacting with? And the reason why this is a particularly nice thing to do is that the reaction coordinate mapping gives us quite naturally two different definitions of heat that we can test. And that's because heat is usually going to be defined as some sort of energy transfer with an environment or a bath. And the reaction coordinate mapping gives us two possible definitions of the environment or the bath. So those two definitions of heat come quite naturally from the two different definitions of environment or bath. So I'm not going to read the full paper word for word, but I do think that there's certain sections which it would be useful for me to read and then maybe explain in a little bit more detail. And the abstract will be one of those. So let's read this now. We say that the definition of heat in quantum mechanics is ambiguous, right? It's not well defined. People disagree about it. Complications in defining heat arise in particular when the coupling between a quantum system and a thermal environment is non-negligible. Right, so what does this mean? It means that the quantum system is strongly interacting with its environment. And then we're saying that as the boundary between the two becomes blurred, making the distinction between the system and the environment difficult to draw. So the way I think about this is, if you've got an open system and it's surrounded by an environment, if they're strongly coupled, then you can't point to a certain part of that system, the composite system, and say that's definitely the environment, but that bit's definitely the open system. Right? The boundary between the two is blurry. And why is that important? Well, because if you want to define heat transfer between two objects, then you probably want to be able to define those two objects distinctly in the first place. Right? Whereas if there's a blurry boundary between the two, then it's going to be difficult to talk about energy crossing between the boundary between the two because the boundary is blurry. So we say that the reaction coordinate, which often gets shortened to RC, mapping can be used in these regimes to redraw the boundary between the system and the environment. So if in our original frame the boundary is blurry, we can perform this reaction coordinate mapping, which I always just think of as like a rotation in some, well, I think of it as a rotation in Hilbert space basically, and we're just we're changing our view of what's going on. That's the way I think about unitary transformations. Now in this paper, we're going to combine this reaction coordinate technique with what's called the 2-point measurement protocol. So this is a way of measuring the statistics of observables, well, maybe not observables, of physical quantities that you can't directly measure. And that's going to be important because it turns out that you cannot directly measure heat. There doesn't exist a heat operator that you can measure. So you need to come up with clever ways of defining heat in terms of things that you can measure. And one way of doing that is with this 2-point measurement protocol. So we combine the reaction coordinate mapping with the 2-point measurement protocol, and we use it to compare two different definitions of heat. So we want to calculate how much does the energy of the environment before we perform the reaction coordinate mapping, how much does that change? Or how about the environment after we perform the reaction coordinate mapping, which is called the residual environment. And I'll cover what happens when we perform the mapping just so that we know what that means. So finally, we find that the latter definition, which is the residual environment definition of heat that we will talk about, displays behaviour more expected of a heat bath in this highly non-Markovian regime that we consider. So I think the issue with trying to define and then calculate heat for quantum systems is the fact that it's a path function, which means that it not only depends on the initial and final states, but also on the path taken between those states. So we talk about that in this first paragraph here. We basically just mention the difference between state and path functions, and then say that because heat and work are path functions, they're very difficult to define for quantum systems. And there's no clear analogue between classical work and heat and quantum work and heat. So we're trying to help bridge that gap between a classical definition of heat and a quantum definition of heat. So defining heat in quantum mechanics isn't all bad. If you have very weak system-environment interactions, then you can essentially just define your heat transfer as any energy which is exchanged between the system and the bath that the system is in contact with. Right, so for very weak interactions, this is a reasonable thing to do. But we're not interested in weakly coupled open quantum systems, we're interested in strongly coupled open quantum systems. And for these systems, using this particular definition of heat is not valid. The reason being is that it's assumed that the interaction energy between the system and the bath is weak enough to be ignored, and if they're strongly coupled, then that's just not the case. We can't ignore that interaction anymore. So let's see what we say here. If the interaction energy is comparable to the internal energy of the system, there's no longer a clear partition between the system and environment degrees of freedom because they're strongly correlated. So that's what we mentioned in the abstract where we talk about the boundary between the two becoming blurry. And if we're trying to define heat, which is energy transfer between the two, and we can't even define what they are individually, then that's not really making any sense, is it? Okay, so this leads to even further ambiguity in defining heat. So if the issue is this separation or drawing the boundary between system and bath, then maybe we could try a couple of different partitions and see what the heat definition, which comes from those definitions of system and environment, we can compare those two definitions of heat and then see which one makes the most sense. So we have some classical intuition about how heat should behave, and for example, so what do we expect? We expect heat to transfer in one direction only, from something hot to something cold. So we can use these two definitions of heat, and this is what we're going to do later, we're going to use these two definitions of heat, and then we're going to see, is it flowing in one direction? If it's flowing back and forth, then that might not be a very good definition of heat, because classically we think of heat as going in one direction, right? That's just the second law. So the way that we do this is by deriving what we call a heat counting reaction coordinate master equation. Now this generalizes the reaction coordinate master equation and lets us calculate what's called the characteristic function of the heat probability distribution. It's just a Fourier transform of the probability distribution. Okay, we also test our definition against an analytical, exactly solvable case, just to show that it's working. But our heat counting reaction coordinate master equation is not limited to only solving problems for that analytic case. Right, so we use our general technique and apply it to a specific analytic case just to make sure that it works, and then we can generalize or use our master equation in situations where there doesn't exist analytic results. So finally, we just talk about the two different definitions of heat, which are just going to be changes in what we call the full environment, which is the environment before we perform the reaction coordinate mapping, and the residual environment, which is the environment after we perform the mapping. Okay, we also then talk about changes in something called ergotropy, which is maximum unitarily extractable work, and changes in von Neumann entropy of the two different definitions of system that we're going to get from using this reaction coordinate mapping. Right, and then finally we just give a brief outline of what's going to be in each section. So section 2 of this paper considers counting statistics in the strong coupling regime. And the first thing that we need to understand is the 2-point measurement protocol, which is section 2.1. But essentially the issue that we have is that we want to gather some information about how much heat Q is transferred between the system and its environment, and that is going to be described by some probability distribution, P of Q. Alright, so let's assume that it has some arbitrary looking shape. What this distribution tells us is, okay, how much probability is associated with a given value of heat transfer. So this is the thing that we're interested in finding, but it turns out that finding this thing is actually very hard. So finding the probability distribution of Q after some time is difficult to do. But what we can do is instead find its Fourier transform. So if we Fourier transform this probability distribution, so we integrate over Q, and we have in a complex exponential e to the I Q times chi, then this will give us something called the characteristic function, phi of chi evaluated at time t. And this is our main object of interest in this paper. Okay, it's possible that I've missed out a factor of 1 over 2 pi. Yeah, exactly, okay. So chi is called the counting parameter, also called the counting field by some people. And what we can see if we look here is that it must be conjugate to heat. Okay, so in section 2.1 of the paper, we leave things quite general. So we talk about measuring a quantity m, which what we actually care about is measuring q. But for this introduction to counting statistics, we keep things quite general. So let's have a look what's going on here. And I think that most of the important information can be deduced from this figure. So we start off in the top left, and we have this open quantum system in blue, and it's interacting with this environment which encloses the system in green. And then I've tried to make it clear that the system and the environment are going to interact by having this sort of dashed line around the system, so that stuff leaks in and out of the system to and from the environment. So the first thing that we do is we prepare an initial state of the system, and we're going to assume that it's in contact with the thermal bath, so it's in the Gibbs state. We then perform a projective measurement onto an observable, which we call M. Okay, so this is a Hermitian observable. And then we allow the composite system, so the system and the environment together, which are a closed system, to evolve unitarily for some time t. And then we perform a second projective measurement onto the eigenbasis of M. So each one of these projective measurements is going to have given us one of the eigenvalues of M as the outcome, and it would have given us one of those eigenvalues randomly. So we now have two random eigenvalues of M, which I'm going to call M0 and MT. Right, this is just whatever eigenvalue we measured at time t is 0, which is defined as the time at which we performed the first measurement. Excuse me. And then MT is just defined as whatever measurement outcome we got at time t, which is when we perform the second measurement. So we then take the difference between these two values, and this is going to be a stochastic quantity, and we call it M. So if we repeat this protocol many, many times, we're going to get a bunch of different values of M, each one being stochastic because it's made up of two eigenvalues which we got randomly through performing projective measurements. And then that's going to let us build this probability distribution, which I show in the center of this figure, PMT, as a function of M. And maybe it has some sort of shape like this. Okay, so that's a very quick introduction to the idea of counting statistics, but I actually made a video about the two-point measurement protocol a couple of years ago, and I go through things in quite a lot of detail in here. So if anyone wants to know more about the two-point measurement protocol, then I would suggest watching this video, and I will perhaps put a link to it somewhere. But anyway, let's have a look at some of these equations here. So in equation 1, we have the characteristic function in terms of the probability distribution. So we can just see that it's the Fourier transform. Right, and then we use this really interesting result by Esposito, which tells us that we can write this characteristic function as the trace of a generalized density operator. So rho of chi and t is a generalized density operator, and what we're going to mean by that is that its trace is not necessarily equal to 1. So it's not a true density operator, but it is going to evolve kind of like one. And that's going to be important and useful. So the particular form of the generalized density operator is given down here in equation 3. And then what we can do is, if we scroll down a bit, so we can take the partial trace over the bath, degrees of freedom, and then we can rewrite the characteristic function simply as the trace over the system part of this generalized density operator like this. Well, why is that useful? Because we can then derive a generalized version of a master equation for that reduced system state, which is what we see in equation 6 here. So we have a master equation for the reduced generalized open system density operator. So how does rho s chi of t change with respect to time? And essentially all that happens is that the Liouvillean, which describes the evolution of the state, gets a dependence on this counting parameter chi. Okay, so why is that useful? Well, because if we can solve this master equation, which it turns out that we can, then we have access to a list of all of these states, which we can therefore take the trace of, which therefore gives us the characteristic function. If we have the characteristic function, we can just inverse the Fourier transform and get the probability distribution that we're interested in. So this idea of using a generalized form of a master equation in order to track this generalized system density operator in order to calculate the characteristic function is really interesting and also really useful, because there's nothing stopping us from using a master equation other than the Born-Markov weak coupling master equation, which is what was used originally by Esposito. And that's good news for us, because if we were limited to only using that weak coupling master equation, then we could only look at heat counting statistics in the weak coupling regime, which isn't what we want to do. We want to look at it in the strong coupling regime. And essentially what that's going to mean is that all we need to do is we just need to generalize with this chi parameter a master equation which is valid in the strong coupling regime. And the one that we're going to do this to is the reaction coordinate master equation. You could also do this with, for example, the polaron or the variational polaron master equation, and that would be interesting to do as well. But we choose to do it with the reaction coordinate master equation here. So we're essentially going to have an equation which is very similar looking to this, except our reduced state is going to be of the extended system, not of the system itself, and the Liouvillean will act on the extended system, and it will be caused by the residual bath. But I'll explain what these terms mean now, because we'll cover the reaction coordinate mapping. So before moving on, we should really just talk about the particular system bath model that we're interested in, which is the spin boson model. So we have a two-level system linearly coupled to a bath of harmonic oscillators, which is going to be described by the Hamiltonian in equation 7. So we've got some energy splitting between basis states, some tunneling between those states, and then we couple through the sigma z operator to creation and annihilation operators in the bath. And then this final term is the self-Hamiltonian of the bath. Also, I should mention, I'm going to use the term environment and bath interchangeably, but they mean, at least in the context that I'm using them, they mean the same thing. Okay, so in this particular picture, where we have a two-level system and it's coupled to a bunch of harmonic oscillators, so I'm going to draw them as such. I'll just draw 4. Right, so we have this coupling between our two-level system and our environment. We're going to call this thing the full environment. So everything that is not the two-level system, we're going to call the full environment. And the reason why we call it full will become clear shortly. So the reason that we're going to call it the full environment is because we're about to perform something called the reaction coordinate mapping on this composite system. So let's have a look at this picture from my PhD thesis, which is a bit of a pictorial representation of the reaction coordinate mapping. So on the left, we start with our open system, which in our case is a two-level system, which is in blue here. And it's coupled to the full environment, which are given by these green circles. So each one of these green circles is a quantum harmonic oscillator. And these thick black lines which link the system to each mode of the bath is supposed to represent the fact that they're strongly coupled in this case. Okay, this is an issue because if we were to try and derive a master equation for this system when it's strongly coupled to this bath, it would be very difficult or impossible to do. And that's because a master equation is going to rely on some sort of perturbation theory, which is going to rely on some parameter being small, which is usually going to be the coupling strength. So if we don't have a small coupling strength, then we can't perform perturbation theory, so we can't get a master equation that we want. Right, so in this case, what we can do is something called the reaction coordinate mapping, which is what's happened in this right-hand diagram here. So essentially what we've done is we've pulled out a collective coordinate out of this full environment, this green bath on the left here. And we've sort of morphed a little bit of all these green modes together into this red one, which we call the reaction coordinate. And the reaction coordinate strongly couples to the system. But notice how the system now no longer interacts with any of the other modes. the only line coming out of the system which represents an interaction is connected to the reaction coordinate. So those two things are strongly coupled together. But then notice that the dotted lines here represent weak coupling between the reaction coordinate and these orange modes here. And the orange harmonic oscillators we refer to as the residual environment. Right, it's what's left of the full environment after we've taken the reaction coordinate out of it. Okay, so why is this useful? Well, what we do now is we basically just draw a box around the system and the reaction coordinate, and we refer to this thing as the extended system. Now what we do is we derive a master equation for the extended system state. Now the reason that we can do this is because the extended system is weakly coupled to the residual bath. So therefore we can use perturbation theory there. Okay, now the issue is of course that the reaction coordinate is a harmonic oscillator, so it has an infinite number of energy levels. So it's going to be difficult to simulate that on a computer. So what we do is we truncate the number of energy levels that we simulate in the reaction coordinate. That gives us a finite dimensional Hilbert space of the extended system, which allows us to solve problems tractably on a computer for the extended system state. Now what's really interesting about the reaction coordinate mapping is that the coupling strength between the reaction coordinate and the residual environment is completely independent of the original coupling strength between the two-level system and the full environment. So what that means is that after we perform the reaction coordinate mapping and derive the reaction coordinate master equation, then we can use that master equation in the strong coupling regime because it doesn't depend, the perturbation theory that the reaction coordinate master equation is based upon does not rely on the original system environment coupling strength being small. It relies on something else, which is essentially that the spectral density of the full environment is sharply peaked. But other than that, we're allowed for the coupling strength between the system and the full environment to be as strong as we like. Okay, so here we basically just give a short introduction to the reaction coordinate mapping. We show what the Hamiltonian looks like after we perform it, and then we show what happens to the spectral density of the full environment, which we originally take to be what's called underdamped, which is essentially a sharp peak like this. And then it's going to get mapped to an ohmic spectral density for the full environment like this. Now, one thing which is really good to know about the reaction coordinate mapping is it becomes more valid the sharper the spectral density of the full bath is. And the reason is because essentially what we're doing when we perform the mapping is we assume that the system only couples to a single mode of the bath, which is the reaction coordinate. So essentially the way to think about this is the more sharply peaked the spectral density is, the more closely it approximates this delta function. And that's why the reaction coordinate mapping becomes even more valid for spectral densities which are more sharply peaked. Right, this is also really useful because if you was to use the standard Born-Markov master equation, that gets invalid for sharply peaked spectral densities. So the reaction coordinate mapping is good everywhere that the Born-Markov master equation is bad, which is why it's a very useful thing to use. So I won't go through all the details here, but essentially this parameter, lowercase gamma, tells us the coupling strength between the extended system and the residual environment. And notice that it is not proportional to alpha, which is the original coupling strength. So it's actually only proportional to the ratio of the spectral density width, gamma, and the peak location, omega naught. Right, and because of this, what it's going to mean is that the reaction coordinate master equation is valid for strong system environment interactions. And by that I mean the original two-level system interacting with the full environment. Okay, so now we've got the prerequisites of the two-point measurement protocol and the reaction coordinate mapping out of the way, we now morph the two together, and this is the main result of the work done in this paper here. So we start off with a expression for the characteristic function when we are trying to calculate the amount of heat transferred between the two-level system and the full environment. So what we've done here is we've taken our general equation for a characteristic function that calculates the statistics of a quantity m, which is, let's see. Okay, so it would be this equation here if we put in this form of rho of chi of t, where we choose what operator m we're performing these projective measurements onto. So let's have a look at what that characteristic function looks like. It's given here. So we take the trace of this term here, essentially represents the second projective measurement that we perform. And then here we have u and u dagger. This represents the unitary transformation between the first and second measurement. And then this term here represents the first measurement. So if we go back up to this diagram, so we had the second projective measurement was the first term inside that trace. The unitary evolution was on either side. And then we had the first projective measurement was directly next to the initial state, which was this part here. Okay, so that's what each one of these terms means. So what's really useful is the fact that the characteristic function involves a trace, and the trace is unitarily invariant. So what it means is that we can put in the identity in terms of unitary operators into this expression. So we insert the identity in terms of this operator, which performs the reaction coordinate mapping. And we basically just sandwich it everywhere in this expression that we can. And then you can see that, for example, we bring them up into the exponentials, we transform the unitary time evolution, and we sandwich the initial state like this. So we're essentially just now calculating these heat statistics of the full environment Hamiltonian in the reaction coordinate frame. Okay, now why is this nice? Well, one thing I should have mentioned about the reaction coordinate mapping is that if I get this picture back up, we've assumed that the mapping has been performed such that the interaction between the extended system and the residual environment is weak. That's what I've tried to represent with these dotted lines here. So if that interaction is weak, that means that to zeroth order, we can just ignore it. And that's what we do in between equations 16 and 17 here. So essentially, what we've done is we've ignored the interaction term between the extended system and the residual environment. So that's what's happened here. Let's see. We assume that the Gibbs state of the full environment can be approximated as a tensor product of the reaction coordinate and the residual environment. Again, that's basically just assuming that the interaction between the extended system and residual environment is weak. Okay, now here comes the really interesting part, which is that we rewrite our characteristic function slightly, and then we take this generalized state and we find how it evolves in time. And we see that it evolves with an equation which is, it looks very similar to the Liouville von Neumann equation, except the interaction Hamiltonian has been dressed by this counting parameter chi. And then essentially what we do is we use this equation as a basis to calculate, to derive a reaction coordinate master equation. And we end up with this thing here, which, if you remember, if we go back up, looks very similar to this form of the master equation, which we saw a few sections ago. Except now, because it's a reaction coordinate master equation, it's tracking the generalized form of the extended system state. So the two-level system and the reaction coordinate together. Right, and then once we solve this master equation, we can collect a bunch of these states, which then lets us calculate this characteristic function here. Okay, there's a small typo there, isn't there? There should be a chi t here as well. So that's how we can use the reaction coordinate mapping to calculate the heat statistics or the heat transfer between the two-level system and the full environment. But it's also possible simply by changing the operator that we perform the projective measurements onto to calculate the heat statistics or the heat transfer between the extended system and the residual environment. And we do that by just going through a pretty similar set of steps. So we just take our measurement operator to be the residual environment Hamiltonian, but in the original frame. So we've just changed it with the mapping which performs the reaction coordinate appropriately. And essentially what we find is that so this is the characteristic function for the residual environment definition of heat, and it's just proportional to some chi-dependent state of the extended system. And it turns out that this state and the one which showed up in the characteristic function for the full environment definition of heat both obey the same equation of motion, which is what we call the heat counting reaction coordinate master equation. Alright, so that's very nice. And then the only difference between them is their initial state into that master equation, which we show in these two equations here, 27 and 28. Okay, so the last thing that we do before we move on to the results section is we say, well, we want to be able to test that this reaction coordinate master equation that we've generalized can give us a result which makes sense and which we can so we want to compare it to an analytical result so that we can say, okay, in this regime, our master equation is doing what it should do. And we can do that because if we look at the independent boson model, which is the spin boson model with no tunneling, then this system is now analytically solvable. And we're also able to find the heat statistics for the full environment definition of heat, exactly in this case. Right, so this comes from Popovich, and we get an analytical expression for the heat transfer between the two-level system and the full environment. So essentially, in the results section, we're going to do two main things. We're going to test the difference between this exact expression for the heat statistics of the full environment definition of heat. And we're going to compare that with our approximate expression for those same statistics, the full environment definition of heat. Now, what we're going to see is that our method, which is approximate but general, works very well when applied to this analytic system. And then we're going to say, okay, well, if it works well in this case, there's no reason to assume why it won't work well if we have non-zero tunneling, so the full spin boson model, which does not have an analytical solution. And then after making that assumption, we're going to say, okay, well, now let's test the difference between our approximate method of calculating the full bath heat statistics with our also approximate method of calculating the residual bath heat statistics. So those two steps are, first of all, check that the master equation works, and then second of all, use the master equation to test two different definitions of heat. And that's what we're going to be doing in the results section next.